In Chapter 12, you learned the basics of radiation. Now, in Chapter 13, you will learn how to apply these concepts to radiation exchange between surfaces. When solving a radiation problem that involves multiple surfaces, you must start out by calculating the view factor. The view factor has a nice descriptive name because it is the fraction of radiation emitted by a surface that can be seen by another surface. The formal definition is the fraction of the radiation leaving surface I that is intercepted by surface J. We denote that view factor as Fij. Similarly, you can probably guess that the view factor from J to I would be Fji. Let me illustrate the importance of this concept with an example. Say you have a very small plate of area dA1 which emits 100 watts of energy and is located in vacuum. Further away, there is another even smaller plate of area dA2. How much radiation is plate 2 receiving? Plate 2 cannot intercept all the radiation emitted by plate 1. Thus, it would be necessary to find the view factor F12. The integral equation for the view factor is the following. This equation is not fun to use at all, but thankfully there are certain view factor rules that can enable you to bypass having to use the integral equation. The first rule is the reciprocity equation, which enables you to use one view factor to find another one. The equation for reciprocity is the following. Another rule is that all the view factors in an enclosure must add up to 1. This makes sense because the total fraction of energy emitted by a surface has to be 1/1. It is possible for the radiation emitted by an object to be intercepted by itself, such as in the case of a sphere. The radiation emitted from one side of the sphere can be intercepted by the rest of the sphere. However, if an object is flat or convex, its view factor to itself will be 0 as it cannot intercept any of its own radiation. With this information, you will be able to solve many view factor problems. Remember, black bodies are perfect absorbers and emitters, meaning that they do not reflect or transmit any energy. Thus, for a black body, radiosity, which is the energy leaving, is equal to irradiation, which is the energy coming in. We can write the following equation for the net rate of radiation for the interaction between two black bodies. In this equation, Qi is equal to Qi to j minus Qj to I, meaning it is the radiation from I going to j minus the radiation from j going to I. So it is ultimately the amount of radiation that is leaving I. Thus, it is also the amount of radiation being gained by j as a result of their interaction. Radiation exchange between non-black body surfaces can be complicated, so we simplify it by assuming that the surfaces are isothermal with uniform radiosity and irradiation. They are opaque and diffuse. The last point here about the diffuse surfaces allows us to use Kirchhoff's law and say that the emissivity is equal to the absorptivity. The following equation is the rate of radiation leaving surface I. These three equations have been related to each other through the use of J is equal to E plus rho g, E is equal to epsilon times E of black body, and rho is equal to 1 minus alpha, which is equal to 1 minus epsilon, because there is no transmissivity and because alpha is equal to epsilon. Qi can also be expressed in terms of other surfaces that it interacts with, using an equation similar to that for black body interactions. The equation is the following. In some cases, it might be convenient to use this equation in the form of a resistance diagram like we did earlier in the semester. Here, Ai, Fij to the power of -1 are the resistances, and instead of temperatures in the numerator, we can use the radiosities. Take a look at the following practice problem. The basic few factor equations we learned are AI times Fij is equal to Aj times Fji, and that the sum of all the view factors for a surface add up to 1. We also learned that flat and convex surfaces have a view factor of 0 to themselves. In part A, surface A1 is made of two flat surfaces that cannot possibly emit energy to themselves, so F11 has to be equal to 0. From the addition rule, F11 plus F12 is equal to 1, so then F12 is equal to 1. Now we use the reciprocity rule in order to find that F21 has to be equal to A1 divided by A2 times F12. We have to find what A1 and A2 are. We can use R for radius and L for the length of the duct to get that A1 is equal to 2RL and A2 is 3 over 4 times 2 pi RL. And so we have solved part A. For part B, it can be easiest to solve the problem by imagining a third area, A3, which is the other hemisphere, in order to turn the outer surface into a sphere. Since the inner sphere cannot intercept any of its own radiation because it is convex, F11 is equal to 0. Then from inspection, it can be seen that F12 has to be equal to F13 and it's equal to 0.5. This is because of symmetry, because all the radiation in the upper hemisphere is the same as all the radiation in the lower hemisphere. So now by reciprocity, we can find that A1 times F12 is equal to A2 times F21. And since we know that A2 is equal to 2 times A1, then we can just write that A1 F12 is equal to 2A1 F21. And we have finished part B. In part C, we immediately notice that surface 1 is flat, and so F11 is equal to 0. Now, either by inspection or by the summation rule, you can come to the conclusion that F12 is equal to 1 because all of the radiation from surface 1 is getting intercepted by surface 2. We can then use the reciprocity rule to connect F21 to F12. Area 1 is 2RL and area 2 is pi RL. Now that we have found F21, we can then find F22 through the summation rule. And so with this, we have solved part C as well.